Hello everyone from Math 2200, Discrete Mathematics. Professor Wenson here again with a video on ZyBooks Section 2.1. This is on mathematical definitions. So Chapter 2 is titled Proofs. Right, you're going to be learning how to write more formal proofs, actually demonstrate with mathematical and logical reasoning that certain statements are true or certain statements are false. And in a lot of the proofs you're going to be writing for this chapter and later chapters, you're going to be using a lot of definitions of terms and writing out the formal definition of things. What does it mean for an integer to be even, to be odd? What does it mean for one integer to divide another? What does it mean for a number to be rational, irrational, stuff like that. There's lots and lots of mathematical definitions out there. But this section here, 2.1, goes into some of the basic definitions. That'll keep coming back throughout the rest of Chapter 2 at least, when we go through this introduction to proofwriting. Alright, so I'll read the opening heading. Many of the theorems in the material about how to write proofs are facts about numbers that can be proven with standard algebra. Theorems and proofs throughout the rest of this material establish facts about a variety of mathematical objects, such as graphs, functions, sequences, and sums. This section contains mathematical definitions related to many of the examples of theorems and proofs presented here. Right? So presented in Chapter 2 of the ZyBooks. This section also reviews some basic mathematical concepts that are useful in the reasoning found in proofs. So the first part about is in this section is what does it mean for two integers to be even or odd? Now I know you know what even integers are. 2, 4, 6, 8, 0, -2, -4, -6, -8, and so on. Those are the even integers. And I know that you know what the odd integers are, right? 1, 3, 5, 7, 9, and then -1, -3, -5, and so on. But here we have a more formal definition. What does it mean precisely to be an even integer or an odd integer? So an integer x is even if there is an integer k such that x equals 2 times k. Alright, so basically an even integer is an integer multiple of 2, some multiple of 2. Alright, and we'll see how that's used in a proof writing in a later section. An integer x is odd if there is an integer k such that x equals 2k plus 1. Right, because if you think about it, every odd integer is just an even integer, 2k, plus 1, isn't it? Right? 3 is 2 plus 1. 5 is 4 plus 1, 2 times 2 plus 1. 7 is 6 plus 1, or 2 times 3 plus 1. All right. So, and these little ways to write, express an even and odd integer are going to be very useful in proof writing. 2k and 2k plus 1. Or 2 times an integer, 2 times an integer plus 1. Alright, some other definitions here. Pardon me. The parity of a number, or parity. The parity of a number is whether the number is odd or even. Right? So if two numbers are both even or they're both odd, then the two numbers are said to have the same parity. If one number is odd and the other is even, then the two numbers have opposite parity. Alright, so some examples relating to even and odd. Is the number 0 even or odd? Let me pull up some paper here. Let me make this a little bigger. Alright. The number 0 can be expressed as 2 times an integer, namely 0, can it? 0 can be expressed as 2 times an integer. So by definition, 0 is considered an even integer. So is the number 0 even or odd? It's type in the word even. So here, number 2, right? Show that negative 73 is odd by giving an integer k such that, negative 73 equals 2k plus 1. Remember what it meant to be odd, right? It meant you could express it as 2 times some integer plus 1. So let's see, negative 73. That's just one more than negative 74, isn't it? And negative 74 is 2 times negative 37. So negative 73 can be expressed as 2 times an integer, negative 37, plus 1. So negative 73 is an odd integer by definition. Now they want this integer k, that the k here, right, would be the negative 37, 2 times k plus 1. So over here I'm just entering negative 37 minus 37 there. Okay. The next one. Suppose that n is an integer. Is the number 2n plus 3 even or odd? Think about it. If you take a number, now remember, if you take, remember 2 times n, that's going to be even. And then what we're doing is adding 3 to it. Think of any even number, 6. Add 3 to it. You get 9, that's odd. Take another even number, 8. Add 3 to it. You get 11, that's odd. 10, add 3 to it. You get 13, that's odd. Now this doesn't prove anything, but it's giving me a good idea that, hey, this is going to be odd, isn't it? Now let's actually show it, right? 2n plus 3, this is the same as, 2n plus 2 plus 1. Right? 2 plus 1 is 3. And then both of these terms here have a factor of 2 in common. So I pull that out. That's 2 times the quantity, n plus 1, and then plus 1. This n plus 1 is like the k earlier. So you see how 2n plus 3 can be rewritten as 2 times an integer, right? If n is an integer, n plus 1 would be an integer. 2n plus 3 can be written as 2 times an integer plus 1. So by definition would be odd. Right? Any odd number, odd integer, can be expressed as 2 times an integer plus 1. Alright, and then do 7 and 22 have the same parity. Remember, parity is whether they're odd or even. So like the parity of 7 is odd, the parity of 22 is even. They do not have the same parity. I would just type in no. Okay. Alright, so that was definitions of even and odd. You're going to use those, 2 times an integer, 2 times an integer, plus 1. Alright, next part of this section, we get into a formal definition of what does it mean for a number to be rational. And you've probably heard this before in some algebra class before or whatever, but here we go again. So some of the theorems proven in this material are facts about rational numbers. And here's the definition. They don't have it in a box or anything. I think they should. But it's bolded, so pay attention to it. Pardon me. A number r is rational if there exist integers x and y such that y is not 0 and r is equal to x divided by y. So basically, a rational number can be written as a ratio of two integers where the denominator is not 0. Or a rational number is a fraction, again, a ratio of two integers where the denominator is not 0. So you gotta keep that in mind. This thing right here is gonna be important, and knowing that the denominator is not 0, rewriting a rational number as a ratio of two integers x and y. Okay. So now the questions related to this. Is 0 a rational number? Does it satisfy this definition? So again, look at the number 0. Can't I express 0 as 0 divided by, any non-zero number I want, like 1? 0 divided by 1, there's like the x and the y. I can rewrite 0 as the ratio of two integers, or a fraction with two integers, and the denominator is not 0. So by definition, 0 is a rational number. So is 0 rational? Type yes or no. Yes. Suppose that r equals 0.677 and y equals 1,000. Show that r is rational by giving an integer x such that r equals x over y. Well, this one's, again, pretty simple if you know what decimals are, right? r equals 0.677. Or you can write any decimal that ends can be written as a fraction, or that repeats as well. You can see repeating decimals can also be rewritten as a fraction of two integers. This ends in the thousandths place, right? Tenths, hundredths, thousandths. So this is equivalent to 677 divided by 1,000. So the x they're looking for, see they told me already the denominator was 1,000. The numerator is 677, but you see how this number can be rewritten as a fraction of two integers, a ratio of two integers where the denominator is not 0. So this number is rational, and the numerator would just be 677. And they do the same thing here. This is just negative 5 hundredths, right? Negative 5 over 100, so negative 5 here. It's very simple with decimals, I think. All right. The next part of this section, another definition you're going to need to know, right? So the definition of even number, odd number, rational number. What does it mean for one integer to divide another integer? So some of the theorems proven in this material are about whether one integer divides another integer. The definition below gives a mathematical expression for an integer n when m divides n. Now when you say one integer divides another integer, that just means the first integer goes into the second integer evenly. So here's the definition. An integer x divides an integer y if and only if x is not 0, because 0 doesn't go into any number, anything evenly when you divide. You can't divide by 0. If x is not 0 and y is a multiple of x, y equals kx for some integer k. So x divides y if y is a multiple of x. That's what they said down here. If x divides y, then y is a multiple of x. And x is a factor or divisor of y, right? X goes into y evenly. The notation is this. Now be careful. This is x with like some vertical bar and then a y. This is not the division symbol. It's not x divided by y. It's x divides y. Big difference. All right. And if x does not divide y, then you put x divides y with a little slash through the bar. All right. So some more stuff here. indicate whether each expression is true or false. So the first statement there is 3 divides 12. 3 divides 12. Basically, the question is 12 an integer multiple of 3? And the answer is yes. Right? You got 12 is equal to 3 times 4. And that's like the k that was being talked about in the definition. Y equals kx, right? Y equals 4 times 3. So yes, this is true. 3 divides 12. The next statement is 5 divides negative 20. So again, same thing as, does 5 go into negative 20 evenly, or is negative 20 an integer multiple of 5? So, and that's also true, right? Negative 20 is 5 times negative 4, right? It is 5 times some integer. So, that's also true. Now, again, the little slash through anything means it doesn't divide. 11 does not divide, right? See the little slash through it. 0. Right. Well, let's look at the opposite. Let's look at, is this true? Does 11 divide 0? Yeah, you can write 0 equals 11 times 0. Can't you? Right. So yeah, I can 0 is equal to some multiple of 11. It's 0 times 11. So yes for this, meaning that this is no, right? This is false. 11, saying that 11 does not divide 0 is false. And again, the explanation there, just what I wrote. 0 equals 0 times 11. All right, and yeah, I'll leave it to you to do the other ones. All right, some other definitions. What does it mean for numbers to? Again, you've probably heard these words before, but we're getting some formal definitions here that we're going to be using in some proofwriting. An integer is, all right, so what does it mean for numbers to be prime and composite? An integer n is prime if and only if n is greater than 1. Okay, so 1 is not prime. Get that in your head right now. 1 is not prime. And neither are negatives, right? This is positive numbers. These are numbers that are 2 or greater. Integers that are 2 or greater. So an integer n is prime if and only if n is greater than 1, and for every positive integer m, if m divides n, then m equals 1 or m equals n. So all this last stuff is saying is that if an integer is prime, its only divisors, the only numbers that go into it evenly, are 1 and itself. Right, and you've probably heard that. And 1 is not prime. And it's not composite either. 1 is like the base unit, the building block. An integer is composite if and only if it's greater than 1, and there is an integer m such that m is between 1 and n and divides n. So basically, if it's not prime, right? If it's not prime, it's composite. And again, these are just for integers 2 or greater. Right? So I've already told you twice now. 1 is a prime number? No. No, it is not. 2 is prime? Yes. It's greater than 1, and the only numbers that divide it are 1 and itself, are 1 and 2. 9 is prime? No. 9 is not prime. It's greater than 1, sure. But there's a number between 1 and 9. that goes into it evenly, namely 3. Right? 3 is between 1 and 9 and goes into this evenly. So this is composite. And I'll leave the last one to you. All right. Now inequalities. Again, this should all be pretty familiar from a basic algebra class or beginning algebra class. So I'm not going to spend too much time talking about this. Just again, you just got some definitions here. Remember, this is x is less than c, x equals c, x is greater than c. You know, if these are real, if you're talking about real numbers, exactly one of these three things has to be true for any two real numbers. They're either one's less than the other, or they're equal, or one's greater than the other. You got the greater than or equal to symbol. It's at least, less than or equal to symbol at most. I'm not going to really read all this to you. This should be pretty familiar. And you can watch the animation here involving inequalities. Like I said, this is all pretty basic. All right, and then another way to write inequalities. All right, let's do a couple of these. Select the statement that is equivalent to each statement below. X is less than -7 or x is equal to -7. Right, you've seen the less than or equal to symbol, I hope, by now. X is less than or equal to -7. X is less than 3 is false. What's the opposite of x is less than 3? All right, remember, this is key up here. You know, all three of one of these three things happen. It has to be happening, and if one of them doesn't happen, then the other two are possible. So if x is less than 3 is false, then either x is equal to 3 or x is greater than 3. All right. So if x is less than 3 is false, then the opposite of this would be true. X is greater than or equal to 3. If x is greater than or equal to 3 is false, right? So if x is greater than 3 is false, equal to 3 is false, then x is less than 3 must be true, right? So the opposite of x is greater than or equal to 3 is x is less than 3. And x is not positive means it's negative or 0, right? Because not positive could be 0 or negative. So less than or equal to 0, and not negative means 0 or positive, greater than or equal to 0. Okay, I don't know why I did all those. All right, and then indicate the truth value of these. I'm just going to do the first one. That's it. If x is greater than 3, then x is greater than or equal to 3. Well, yeah, because if you're 4, 5, 6, those numbers are greater than 3. They're also greater than or equal to 3 because they satisfy the greater to part. If x is less than or equal to 4, then x is less than 4. Well, no, what about 4? 4 would make the hypothesis true, but the conclusion false. So this isn't always true. This is false when x equals 4. And I leave the rest to you. The inequality stuff should be familiar to you. In fact, all those, even odd numbers, prime composite numbers. Now, maybe the only thing that might not be familiar is that divides symbol. Right? When one integer divides another, it means it goes into it evenly. All right. All right. Then you have your additional exercises, which again I put some of these in the assignment 2. Do those with your assignment 2 and upload them, via Canvas, and you can see the solutions here. You can reveal the solutions. So again, I please do the problems first on your own. Try to do them on your own first before you go looking at solutions. All right, because if you just go looking at and copying solutions, you're not going to learn anything. And even try to do do the ones that I didn't assign as well, right? Just to get more practice. Can't hurt. You can only get better. All right, so that's it for 2.1, the intro to Chapter 2 here, mathematical definitions, and thanks for watching.